All right, this is part 2 of Write the Chemical Equation from our the next set of videos. Again, you might want to go back and look at those videos again just to kind of refresh your memory as to what that looked like, although I'll be describing it here as we go through this. The first one here is decomposition. So decomposition is the key characteristic of a decomposition reaction is that you have only one reactant. This time, that one and only reactant is hydrogen peroxide. This one looks a little strange. It may not look like a decomposition because I did add something to the hydrogen peroxide, but what I added is called a catalyst. I believe it was sodium iodide or potassium iodide that I added to that. Well, all that does is speed it up. It really does not participate in the chemical reaction. It just speeds it up. Hydrogen peroxide loves to decompose. That's why it's in a dark bottle like it is, because light can actually cause it to decompose. In the video, I talked about that weird-looking accordion bottle, it's called, that's allowed to expand because that high concentration hydrogen peroxide, if it starts to decompose, if it sits on the shelf long enough and slowly decomposes over time, it can actually build up enough gas pressure to blow up a bottle. So that's why that bottle has that weird shape and it's allowed to expand. Anyway, we want that reaction to take place quickly within just a few seconds. So that's why we add the catalyst. Sometimes what they'll do is write CAT over the top of the arrow like this to say, to show that a catalyst was used to speed this along. But we're not going to worry about that. I'm just gonna take that off, so we're not going to worry about that. All right. So again, decomposition means one reactant is breaking up into multiple products. So first of all, we had liquid hydrogen peroxide, and that is breaking up into a couple of different substances. Now, if you remember in the video, this is the one that got all foamy. I added the hydrogen peroxide to the big graduated cylinder. I also added some dish soap. That was to make it nice and frothy and foamy, and I added a little color just to kind of add a little life to it. But anyway, this is the one that's kind of shot out that foam out the top there. And of course the foam is created because a gas is given off. And I tried to give you a hint as to what that gas was by lighting a wood splint and poking those bubbles a little bit with the wood splint. And you may remember that that gas does not really burn, but it causes the flame on the wood splint to flare up a little bit. In other words, it's not really the gas that's burning, it's the wood that's still burning, but it burns a little bit better when it hits that gas inside those bubbles. And what I was trying to get you to see is that gas is actually oxygen. Oxygen supports combustion, right? It supports the burning of something. You have to have oxygen around if you're going to burn something in that kind of way. So that gas that fills up those bubbles is in fact oxygen. And the other thing you might have noticed, and I don't know how well this showed up on the video, in person you can see it pretty well, but there's lots of steam given off. And that steam, of course, just like any other steam, is, of course, water. So our other product then is actually water. And even though it's steam and it's hot, it's actually in the liquid state. So that is our decomposition, where we have a single reactant that breaks up into multiple products. And now we have to balance the equation here. So let's see here. We've got 3 oxygens on the product side and only 2 oxygens on the reactant side. But because of these 2 subscripts here on the reactant side, we know everything's going to have to be an even number. So the easiest way to even this up is to try to put a 2 there. That kind of evens the number of oxygens. Now we have 4 oxygens on the product side, right? 2 here and 2 here. That's 4 oxygens. So I can get 4 oxygens over here by putting a 2 in front of the peroxide. And that gives me 4 oxygens and also 4 hydrogens, which I also have 4 hydrogens over here. So now that one is balanced. Okay. And our last reaction was actually kind of 2 reactions. I sort of cheated a little bit because I used the burner, the Bunsen burner, as one of the reactions. But it is technically a chemical reaction called a combustion. We had 2 different combustion reactions. Combustion reactions are the ones that are the most sort of prescribed. Combustion reactions are going to involve some compound that contains carbon and hydrogen. In this case, it is just simple old methane, CH4. And then that hydrocarbon, that carbon-hydrogen compound, is going to react with oxygen. It's always going to react with oxygen. It is burning in oxygen gas. The CH4 is also a gas. And the products here on a combustion reaction are always the same. If you know it's a combustion reaction, right away, you know 3 of the 4 parts without even thinking about it. Okay? And what I mean by that is, if it's a combustion reaction, it's going to be something reacting with oxygen, and it's always going to produce carbon dioxide and water. Those 3 parts are always going to be part of a combustion reaction. So I'm going to jump ahead, and I'm going to cheat a little bit, and I'm going to go ahead and write that in down here. We've got another combustion reaction down here. So because it's a combustion reaction, I already know that this has to be part of it. It's going to look just like that. I just have to add the hydrocarbon. All right, I'll get back to that one in a minute. Let's go back up to this methane. So we've got a hydrocarbon reacting with oxygen, producing carbon dioxide and water. So now we just simply have to balance this out. So let's see, the carbon's okay. I've got 1 on each side. Hydrogen, I've got 4 over here, only 2 on the product side, so I can put a 2 in front of water. That gives me 4 hydrogens, but it also gives me 2 oxygens here with the water. But I've got another 2 oxygens over here with the carbon dioxide, so I need 4 oxygens altogether on the reactant side, so I need a 2 right there. And that should be all balanced. Okay? So that's a pretty simple one as far as combustion reactions go. That's about as simple as it can get. This next one's a little more complicated, and one reason it's more complicated is because our hydrocarbon here is not just a simple hydrocarbon, it's actually an alcohol, which means one of the hydrogens has been replaced with basically a hydroxide, an OH group. And so it looks kind of funny to write it that way, separating the hydrogens like that, but that's because they write it like that so you can recognize it as an alcohol. Okay, but we've got the same basic structure again. Something that contains carbon and hydrogen reacts with oxygen, produces carbon dioxide and water. Okay. Now, what makes the balancing here a little bit more complicated is this pesky little oxygen right here. It's easy to forget that one's there or not count for it. Okay, so let's go ahead and just start balancing it and see what we figure out. All right, let's look at the carbons first. We've got 3 carbons on this side, so I probably want to put a 3 there. And I've got hydrogens, but notice they're separated, right? I've got 7 there, but 1 more there. So a total of 8 hydrogens on the reactant side. And so to get 8 hydrogens on the product side, I need a 4 right there. Okay? Now let's count up the oxygens here. I've got 3 times 2 is 6 oxygens, plus 4 times 1 is 4 more. So that's a total of 10 oxygens on the product side. But here's the problem. I can't get to 10 oxygens over here unless I start changing numbers here a little bit. In other words, if I put a 5 here to give me 10 oxygen, whoops, I got another one there, so that's 11. So that's not going to work. Usually what the solution is here, what you have to do in this situation is you have to kind of start all over. And what I mean by that is, let's back up here and get rid of these coefficients that I put on there. Whoops, there we go. And then we're going to go back out to the hydrocarbon and put a 2 in front of it. If you get stuck on one of these combustion reactions, oftentimes the answer is to go out and put a 2 out in front there. Now, don't do that automatically because a lot of times you don't need it, but sometimes you do. If you get stuck, you might try that. So now let's look at it again. If I've got 2 of these isopropyl alcohols, that means I need 6 carbons on the product side. And now I've got 16 hydrogens over here on the reactant side, so that means I need 8 waters. And now let's count up the oxygens on the product side. I've got 6 times 2 is 12 oxygens from the carbon dioxide, and I've got 8 times 1 plus 8 more oxygens over here, and that means a total of 20 oxygens on this side. And so to get 20 oxygens on the reactant side, Well, remember, I've already got 2 here, right? 2 in front times this 1 here. So I've got 2 right there, which means I need 18 more from this guy right here, which means the coefficient here is actually a 9. So again, that one's a little tricky. They can get to be big numbers. We're not used to probably having coefficients that are big like this. Usually our coefficients are, like 2s and 3s and even 1s, right, where we don't even have to write a coefficient. On these combustion reactions, they can often get to be bigger numbers than we're used to. All right, let me know if you have any questions with these. Like I said, Monday we are going to have Zoom sessions, and I hope everybody can join, and we'll go over that part 3 and write the equations out for that and have a chance to kind of discuss it a little bit. Hope to see you then.